Romies.
The Romies.
Yeah, they run FRC code.
Yeah. It's like
It's really cool.
$100 for the kit. You put a Raspberry Pi on it. And
You guys get, no, ours came with some.
Was it?
Yeah. Oh, wait, yeah. Hardware was in 2019's game. I forgot. It just straight up read.
Wait, no, actually, we didn't want that. No. We have to wait for it to come down and make the view. Yeah, we wanted that because it came out. Yeah, you're already using it. I don't know if actually, I guess the mic isn't.
You should be able to, is there not an audio indicator on the Meet?
Hello. Okay, yeah, it looks like it's working. Oh, and you guys can hear it a little bit louder. Now the projector is showing the wrong one. Yeah, look, it's showing the wrong one. No, wait, Jason, I meant.
Alright, so I guess we're ready to get started. So thanks everyone for coming to the Kickoff Controls Workshop.
We're still going to resolve some technical difficulties first.
I can move over. Move the slide.
Oh, okay.
We good?
Yep. Cool. So today we're going to talk about some of the following topics. First, we're going to talk about differential drive robots, which are the class of robots that pretty much every tank drive FRC robot is. And then we're going to talk about some of the useful things you can do with controlling these differential drive robots.
We'll start with these building blocks, which you can use in order to make your own autonomous programs for the game. Odometry and localization being like the core of solving a autonomous movement challenge, which is, how do you get the robot to know where it is? So we're going to cover odometry, localization. Then we're going to move on to PID control, which is the control algorithm you can use to position a robot in some certain way. And lastly, we're going to talk about waypoint following, which is how you can get your robot to go through some sequence of points in a neat, smooth way. And for all of these topics, we're going to have some interactive code notebooks. I know we didn't say it before that you guys should bring laptops. If you have laptops, they would be useful for you guys to
Run the code notebooks, but this presentation will be made available to you guys afterwards. If you want to go home and do it on your own, you can. And we're also going to pull the interactive code notebook up on the screen so you guys can see what's happening. And we can have some classroom interaction where you guys can talk about what you think is happening in the algorithms. So before we talk about the actual technical content, I can introduce myself. My name is Varun. I'm a MS-ECE student, Master's in Electrical and Computer Engineering. I did my undergraduate in electrical engineering here at Georgia Tech. I was formerly a student, also formerly a volunteer, also formerly a mentor of FIRST Robotics.
And joining me is Jason. Jason, if you want to introduce yourself.
Okay. All right, sure. Well, this is Jason. He's a PhD student in robotics in the computer science department. He did his undergraduate in computer science as well, and he did FTC in high school. And lastly, I'm joined by Sumaid, potentially MSCS in 2023, but current bachelor's in CS in music tech at Georgia Tech, and formerly on FRC 1261. So now I'm going to give you guys a brief introduction into what we're going to be talking about today. So every FRC autonomous can be broken down into these basic tasks. You're going to start in the location that you place the robot at the beginning, and you're going to want to go to some particular location on the field, do something there. In this case, it would be shoot the balls or maybe pick up the balls from the ground.
Then you'll go to point B, and you'll do something else. So an FRC autonomous consists of, as you can see in this example here, going somewhere, performing an action, and essentially stringing these move, do something building blocks together.
So this is just a demonstration of the robot drives to a point, picks up the ball, drives to another point, shoots the ball, and these motions
Are just strung together in order to create an autonomous that lasts the whole 15 seconds. So in order to do that, what does the robot need to be able to do? The first thing is it should know where it is, and then it should know where it needs to be.
And how do we accomplish that? We have various sensors that are mounted in the robot, the encoders, the IMU, the inertial measurement unit, and the camera. That'll let the robot know where it is and where, the objects of interest are.
Then it needs to decide where should it go, like how does it get to those points.
And that is where path planning comes in.
And so in order to follow the path, the robot's going to need to apply the correct amount of power to the motors. And in fact, if the robot gets off of the path, it needs to apply corrective power to the motors so that it gets back on. And so we call that control. So with the sensing, path planning, and control, these are like the three building blocks for creating autonomous behavior for your robot.
So each of these, you can actually use each of these tools on your own. Maybe in this one season, you don't get to implement all of the things that we talk about today, but it's, as long as you can get one of these steps done at a time, you can combine these in whichever way you want, or you can work with whatever you have and still get some functionality to your robot. You don't have to have every single part of these things put together in order to have a functional autonomous. Even half of it is good. There's a lot of built-in stuff in the WPI lib that can help you out. It wasn't like that when I was a high schooler, but it certainly is the case now.
You can use the WPI lib examples, and you can use other teams' code in order to learn this stuff. But the one thing is when you're writing your own code, it's best to have a solid understanding of the math, because that is what helps you debug. If you make a mistake, and you can't just be blindly changing stuff, you'll waste a lot of time in your debugging. Whereas if you had an understanding of where the formulas come from, you can easily say like, oh, if I made a mistake here, the end result would look like this.
And so our goal is to help you understand the math so that when you implement these on your robot and you see something going wrong,
you can use your stronger theoretical foundation in order to debug faster. Well, in order to deliver this theory to you guys, we need to give a little bit of baseline math. And since you guys have already said that you have some familiarity with, algebra geometry, the thing that we're going to talk about today in particular is vectors. So have you guys ever heard of vectors before? I don't know if this is covered in, geometry. Maybe it's covered in pre-calc.
Yeah. But vectors are like mathematical objects. You could consider them collections of numbers. And since we work with robots which are moving on a 2D plane, they're moving on the surface of the field, they're generally pairs of numbers stacked in a column. So you can see we have u and v are two vectors, and u is comprised of x1, y1, and v is comprised of x2, y2. So like a vector is a collection of numbers.
And, well, another way to think about it is it's a directed quantity.
So it has a magnitude, which is like the length of the vector, and it has a direction, which is, whatever direction that's facing. There's a lot of ways of thinking about it. You could think of it as like motion in the x and then motion in the y, like an x component and a y component, or you could think about it as magnitude and direction.
So the magnitude of the vector is its length, and the direction is the angle between the vector and the x-axis. So you can see we have formulas here. The double bars symbol
Means the magnitude.
And the theta is the symbol for angle. So the double bars is the magnitude, which is the square root of all those components. You get that from the Pythagorean theorem.
And then the angle of the vector is the inverse tangent function of the y component over the x component. So lastly, we're going to define something you can do with vectors, which is called scalar multiplication. So if I did 2 times this vector u, it would be equivalent to doing 2 times x1, 2 times y1. So that's just what scalar multiplication is. You multiply it by a regular number, and it multiplies each of the components by that number.
So now we're going to talk about an important type of vector called a unit vector. A unit vector is just a vector with length 1. And since the length is 1, we can just say, oh, we don't care about the length, we only care about the direction it's facing. So unit vectors are a really useful way of defining directions of just things.
So the unit vector, the symbol for it is a little like pointy thing called a hat. So u hat would be a unit vector. And on the right we have a formula for converting any regular vector into a unit vector.
And to do that, you just take the vector and you divide it by its magnitude. This is just another example of scalar multiplication, right? You divide each component in the vector by its magnitude, and you get a unit vector, which is pointing in the same direction but has a length of 1. And lastly, we talk about how do you multiply two vectors together? There are multiple things that multiple ways of interpreting that statement. The one that we're going to be using today is called the dot product. The dot product is one way that you can multiply two vectors. And in this case, this is the dot product, it's u dot v. And remember that u is x1, y1, and v is x2, y2. The dot product is just multiplying all the corresponding components and then adding all those products together. So this is the definition of the dot product.
And additionally, the dot product can also be represented as the magnitude of u
times the magnitude of v. Remember that these are just numbers. And then multiplied by the cosine of the angle between them. So the dot product of two vectors which are in the same direction is what? Can anyone answer? If the two vectors are in the same direction, what would the dot product be? It would be the product of the magnitudes. Because if they're in the same direction, the angle between them is 0. And so the cosine of 0 is just 1, and so it becomes a product of the magnitudes. So using this formula here, you can actually do this other thing called scalar projection. And scalar projection is finding the length of one vector in the direction of another. So this might sound confusing, but this diagram here pretty much sums it up. So if you have these two vectors, A and B, the scalar projection of A onto B would be if you just drew this dotted line from A onto B, and then you measured where the dotted line intersects the beginning. And this is dependent on the magnitudes of A and B, as well as the distance between the starting point. Or it's like dependent on the magnitudes of A and B, and is also dependent on the angle between A and B. In this case, if B is a unit vector, then the scalar projection is just the length of A that is in the direction of B. So that's a pretty useful tool, and we're going to be using it later in our presentation when we talk about how to track the position of robots on the field. So now we're going to talk about odometry and localization, and for that I'm going to hand it off to Jason.
Jason, student. We're going to kind of go through this a little bit slower. Feel free to interrupt me with questions at any point. We're going to try to focus more on the intuition rather than like the theoretical math, at least for a little bit. So try to understand the big idea, because some of the equations are a little confusing. Don't worry about it. So what are we really trying to do when I say localization? Is anyone familiar with the word localization means? The answers are here on the slide. Where's your robot on the field? Exactly. We're trying to figure out where we are on the field. Why do we care about this? Well, because we want to score points, and we don't want to stay in the same spot. But we can't score points if we don't know where we are. So how do we figure this out? So this is kind of the idea of localization. And you can do this on an FRC field, but I also do it in my research when we're doing like off-road autonomous driving. So to do that, we define the field as some sort of coordinate system. So you guys have probably done coordinate systems in math class before. You have your grid, you have your x, y, you have some point on that xy plane. We know where that is relative to the origin. This is really great. So we can just take that, put it on our field. We have our coordinate system down here. So we have this xy at the bottom. And that's their X direction, that's their Y direction. We put it at the bottom left corner, that's 0, 0. Great, problem solved. We have a coordinate system. As long as we know where our robot is in the coordinate system, we know where it is on the field. Cool, super solved all the problems. So we have our differential drive robot. So this is the representation of that. And what do we tend to get is we have velocities in both the left wheel and the right wheel. These are driven independently. And using those two in some equations, we can figure out how we're moving in the XY plane. But there's some slight issues. So the sensors we're going to use are encoders. So we're going to count the number of ticks on a left wheel or a right wheel. So essentially how far we've traveled on each one of those wheels. We have our IMU that can give us accelerations as well as, my understanding is you guys get out directly yaw. So like the orientation of your robot on the XY plane. Usually you don't get that, you usually have to integrate for it, but it's fine. So use the gyroscope. But what are the important things about these sensors? So if we go back a couple slides, we want it in the global frame. So this is where it is on the field. What are these sensors giving us? It's giving us how far forward we've traveled. And forward is defined based on where the robot is, not where it is on the field, but it's in the frame of the robot. So I can tell things like, oh, I drove forward 1 meter. Well, depending on where my robot is in the field, 1 meter forward can mean very different things. So that's what we're going to talk about here. Let's skip that slide. And so this is what the idea of a local coordinate frame. So a local coordinate frame is, now we have a coordinate frame defined on a robot. So we have that same XY plane, but now it's defined exactly where a robot is. And the way you're going to typically define this is the X direction will be forward and Y will be to the left. And that will give you a positive rotation towards the left and a negative rotation to the right. So another way to think about this is you have this graphic here. So you have like a ship. And the ship defines a coordinate system on itself, so all the sailors can talk to each other and know what they're talking about without saying like, oh, it's to the right or to the left. Because if you're coming from the front of the ship to the back of the ship, right and left are opposite than the other direction. So they define these coordinate systems like this. This is a great example of a local coordinate frame. So this is where all of our sensors will come in this local coordinate frame. What we're going to need to do is take that and transform it into the global reference frame, which is where we are in the entire field to figure out what's actually happening. Any questions? This is like one of the harder concepts in robotics, abstract concepts. So congratulations, you're all undergrads now. One other thing to talk about, so when we talk about angles, we talk about our yaw angle. So that's our orientation of the robot, where we've essentially what direction we're pointing. So we define this usually in radians or degrees, because it's an angle. And this is defined from negative pi to pi or negative 180 to 180. And the reason we do that is because we like to make things hard for you. And it's just trying to be difficult, and it's really nice if it's discontinuous, and it goes directly from pi to negative pi. Right? No, not quite. No, it's actually because this is how it works with geometry. So all of our cosines and sines actually end up working out. So now that we talked about local coordinate frames and global coordinate frame, so we have our global coordinate frame in the bottom left, and then we have 3 different orientations of our robot. And as you can see here, this is what I mean by the difference between a global and a local reference frame. So the local reference frame is centered on the robot. Wherever the robot is currently facing, that's the direction X is in, and the direction Y is to the left. So on the first one, it's pointed like 45 degrees. The next one, it's like flat, and the next one is pointed down. So as our robot moves, our local coordinate frame will change. But our global frame, our global frame will remain in the same spot. Oof. So no matter where we are, the global frame will be the same. And we can always transform things back from the local frame to the global frame. And then if we accumulate things over time, you can figure out exactly where your robot was the entire time in the global frame. So the way we can do this, I said rotation a couple times, is you can use this thing called a rotation matrix. This is it just written out. So if you had some X and Y position, given some theta, you can then rotate that X and Y from the local to the global. And so what you had here, if like taking the first one, what you actually want is what the X in the global and the X in the Y in the global. Then you can take some change in the local coordinate frame and transform it into a change in the global coordinate frame using these coordinates. Any questions? Cool. So kind of the pseudocode of how my understanding of a lot of FRC teams do localization is we take wheel displacement measurements from the encoders. Then we're going to measure some theta from the IMU. You can calculate this also from wheel displacement. As you rotate, you can figure out what that is. Then we're going to compute R, X, and Y. So this is like the radius of curvature, the X and Y change in the local frame. You can then rotate that into the global frame. And then when you have that, you just accumulate it, and you can figure out where you are in the global frame. And this is the basic idea of how odometry is done in FRC as well as robotics as a whole. And this has some error. People have noticed, like, your wheel encoders can slip, your wheels can slip, and things will get a little bit off. But this is a pretty good way to get a general estimate of where you are in the world. So there are some implementations that already exist of this, as far as I understand. And it computes essentially the position of your robot. So WPIlib has things. And some practical considerations that don't exist in the real world, or do exist in the real world that don't exist in theory. Usually we assume no slip when we do these equations. So you're going to slowly accumulate error over time. That'll be proportional to the time that you're doing it. And then you also have limits on how fast you can speed up or slow down. So that covers most of odometry. So what have we covered so far? Essentially, where a robot is in the world. And now that we have that, we can do other things. So when I was a young kiddo, when I was a wee lad, I would want to have my robot do something like this. I want to go straight, take a left turn, go straight, take a left turn, go straight. So I would code, and I would sit there, and I would figure out what the correct motor voltage was to give my correct PWM value, figure out the correct time or the correct number of coder ticks, and then I'd play it. And I'd get something that looks like this. And then I'd spend an hour tuning it, and I'd get something that looks like that. And then I'd tune it again, and then it looks like that. Why is it not matching exactly what I'm wanting? And I can even then do the whole thing over and over again, and then just run the same code exactly, and I still get the same thing. It changes. So what's really happening here? Why is this occurring? See, these are all the things that we're not modeling. So we're going to look at this PID notebook, and if you guys have laptops or whatever, if you can go to that website, you can type it in, I think.
I'll type it in chat as well.
Yeah, that'd be great. You might have to connect to Google Apps.
Do I have to like do something specific to get it?
I think so. Try to connect.
Wait, can you put the link back up?
It's
tinyurl.com/PID notebook.
Yeah.
And
yeah,
it's capitalized.
Yeah, capitalized N.
no. Awkward.
There we go.
Okay. So the first thing we're going to do is if you can go to runtime and then just hit run everything. And it'll probably give you a warning just like that. Just ignore it. I promise you I'm not trying to scam you or whatever. And we're just doing this because I don't like how notebooks work and I get confused what's happening. So we're just going to run the whole thing and then we can rerun certain parts and it's not going to be a problem. I want to zoom in a little bit on the notebook too. So all we're seeing here is like a Python implementation of a PID controller. We're going to have some basic system, and the system we're going to be using to model is like a motor system. So this should be really similar to what you'll see in behavior-wise on your FRC robot. So we've run some of this code, so you can scroll down like all the way to the first prompt. So what we're going to do here is we're going to do this thing called open loop control. So for open loop control, that is just we set the motor command. This is what I was doing earlier. That was not giving us good behavior. So if you scroll down a little bit. We're going to have a fun time with this. So what you see here are axes, and the left one is position, the middle one is velocity, and the final one is the actual voltage that we're commanding to the motor. So if we just set a flat command to the motor, what you see is that our position continues to increase. We're applying some forward velocity, and our velocity increases and then eventually caps out. And this is the kind of the behavior you'll see with motors. So now what we're going to try to do is figure out, I want to stabilize at 1 meter, which is in position. So I essentially want the blue line to match the orange line on the far left plot. What motor value will do this? So the current one we're using is 0.2.
0.
0? Okay, let's put in 0. And then you can just hit the rerun button.
I thought it was
So what happens?
1.
They don't move, right? So we can try 1. So now we stabilize at 2 in velocity, but our position is not stable. So what are we actually controlling here? What does velocity correspond to? Corresponds to velocity. So like we're saying that voltage corresponds to velocity.
I'm confused on what you're asking.
Essentially what I'm asking is we're putting in some control. What we're changing is velocity, right?
Right.
We're trying to set one velocity command or one voltage command and get out a constant position. What's the problem here?
Well, the position is always changing. The velocity will max out, but the position is always,
exactly.
always moving.
You'll reach a steady state with velocity, but your position will continue to go up. So there's no single command I can give the motor that will both move it and then also keep it in the same position. So I can't command it position directly with this algorithm. So now if we go to the next one, we're going to do is more what you see when you actually do things. So I added a little bit of artificial noise here. We can just look at this plot. So you have the exact same position, velocity, and voltage. I put in the same voltage, but now you kind of see that our actual velocity is a very jagged line. And this kind of is simulating like friction or loss of traction or whatever weird things your robot's going to hit. One time, my year, we had a ramp that we had to go up, and that just screwed everything. And then if we keep going. So now what we're going to do is try to stabilize at a velocity. Now, what motor command will stabilize at a velocity? Which one can I pick? So I want to stabilize my velocity at 1. What motor command should I give to stabilize at 1? Because remember, if we set a specific voltage, so if we set a voltage of 0.2, we get out a stable velocity of 0.4. So what's the relationship between this number and this number?
2 times
2 times. So if we want to stabilize at 1, what voltage should we put?
0.5.
0.5. You'll have to scroll back up. Yeah, you don't have to rerun, just rerun the one. Oh, actually, you do have to rerun that.
Yeah, but you can see it's
The velocity stabilized at 1.
So now our velocity is stabilized at 1. So that's great. So now if we go down one more, and you run this one. So previously our velocity would stabilize at 1, but now once we add noise back into the system, it doesn't stabilize at 1. It'll kind of oscillate around 1, but we can't actually get it to 1 exactly. So if we want it to go exactly 1 meter per second, it's not going to work. So this is kind of the idea of what we're trying to do today. We're going to talk about a PID controller, and what it's going to allow you to do is take in something that looks more like this and kind of actually track something, even a position or a velocity. So you jump back to the PowerPoint, yeah. And then click forward one. So what we're going to be using here is the PID controller. So essentially we put in some goal, and this goal can either be in position or velocity. It can really be in anything that relates to your state. And then we're going to compute some error. So we have some sensor reading, like here it'll be the encoder. And figure out what's the difference between our encoder reading, so what our velocity, our target velocity is, and what our velocity we think our velocity is, so our state. We put that into our PID controller, and it's going to tell us what voltage we should be putting out, rather than us trying to pick the correct number arbitrarily based on all these conditions we can't control. That'll get sent to the motor. That'll actually work through the mechanism, and once we do that, we get another reading, and we just repeat the whole process over and over and over again. So this is the concept of like feedback control. So you're closing the loop here. As you can see, we have a loop. It is a closed loop. There's nothing like jumping out. Next slide. So the first thing we have is a P controller. So wouldn't it be nice if we could say that maybe the difference compared to our input voltage will be based on the error between what we want and what we're seeing. This is a P controller. So we go back to the notebook. Right here. So now we have the same before. So UFF here is going to be our feed-forward control. That's what we were doing before, was just like what's the static voltage we want. And then we have some KP, which does our equations. So we take the error, multiply it by KP, and add that to our control. And that's the control that we're returning here. So if we set P to 1, and then run it. So what you're seeing here is the same plots that we saw before. And Google Colab really does not like plots that are bigger. So you have both no noise at the top and then noise at the bottom. And as you can see here, now we're oscillating around our set point. So I want to stabilize at a position of 1, but using my current P controller, what I get is some behavior like this. I go over it, I go past 1, I go below 1. I go past 1, I go below 1. And as you can see here, it's kind of, the oscillation is decreasing over time. So if I just let this do this for infinity, it would actually stabilize. So this is great. We didn't have to pick a feed-forward control at all. All we did was set P equals to 1, and it stabilizes eventually. So what happens if we set P too high? Before he does it, what do you guys think will happen if I set P high? I know you know. Come on, guys.
What are his choices? If he says, by changing P, what things will change?
Oscillation sounds.
Yes, so the amplitude will increase. So if we set P to, we said it's like 2? No, it's 5 works, 5 works. And then we hit run, what we see now is our oscillation is increasing. It's stabilizing faster though. So maybe this is what we want. Maybe this is the behavior we're seeking. I mean, probably not. I don't think anyone wants to see the robot go like this, but it'd be a lot of fun. That's cool. So P controllers are pretty good, but hard to stabilize, right? This is the basic idea of P. So the next thing we're going to talk about is PD. So this D stands for derivative. If you don't know calculus, don't worry about it. Essentially what I'm talking about is the difference in the error, so the change in the error. So now we have our P, which is proportional to the error at the current time step, and then we have D, which is proportional to the change in the error. So if I have a P controller, I'm going to start going up like this. My error is large, I move up like this. But since my error decreases over that time, I damp out using the D term. So if we go back to the notebook, let's go down. And then set like P is equal to 5. And then D is equal to 1, I guess. So this is a P of 5 and a D of 0, so just like we had with the P controller, and you see this oscillation. We quickly get to our set point though, which is nice. We're getting there faster. But now if we change D to some larger number, what do you think is going to happen? Hard to tell. You can do it more, like 10.
So what do you think is going to happen if he changes it to if he changes D to 10?
Yeah.
The amplitude will shorten.
Yeah. So it should stabilize quicker. So as you can see here, it's kind of hard to tell, but between these two iterations, as we increase D to like 50, the oscillations are damped out. But we're still reaching that set point really quickly. So this is kind of good behavior. And as you can see here, this is much better. So not only the oscillations decreasing, but there are also like less of them overall. We quickly reach our set point with this PD controller, and this is really nice. Yeah. So this would be like a really well-tuned PD controller. It would be hard to get something that looks like this, Because you see we essentially immediately jump to our set point, and then we stabilize there, like really quickly. I'm cheating here because there's no actuator limits, so we can like command infinite velocity, but
The voltage spikes up to over 80.
yeah.
What does that mean on your robot? Brown out.
Yeah.
Yeah. Well, since you guys have 12-volt motors, you cannot ask, or 12-volt motors and 12-volt batteries, you cannot ask the motor controller to give more than 12 volts because the power source is only 12 volts. So that's where the actuator limit comes into play in your real-life robot exam.
Okay. Go back to the PowerPoint. Sorry, this is a bunch of jumping back and forth. We apparently didn't plan this well. The next thing we have is a PI controller. So we had before the PD worked pretty well for the application we were talking about. But if you were trying to stabilize in velocity, you would have a little issues with the PD controller. So what a PI controller really is for steady state error. So if we ran a P controller, we'd eventually cap out at some point, and usually that's not exactly where your set point is. So the integral allows you to do the last gap there. And what that's gonna do is it's gonna sum over the error. So we're just doing this running sum of error, which is what this giant formula right here means. So we sum over the error and we just multiply that by some constant as well. So this is the I part, the integral part. So we can show what that looks like. Set P to anything, like 1. So we have our P controller set to 1. Now if I add in an I term, like set like I to 1, what do you guys think is gonna happen? Is this gonna behave well or poorly? Think about how P and I are P and I gonna tell it to move the same direction or move opposite directions? Opposite?
Same, right?
Same.
It's you.
So you're integrating the error and then multiplying it by a constant versus just taking the current error and multiplying it by a constant. So they'll, at least initially, they'll move in the same direction, and then once you cross the set point, I will probably tell you to keep going up because it's accumulated error, but P will tell you to go down. So what you'll see is much worse oscillations. Well, this will probably go crazy. So it just goes unstable. It reaches some set point, and then you can see that it just yeets off the page. And as you can see up there, it's 1e to the 14. So that's a really large number. That's a really fast robot in 20 seconds. So if we have a lower I, what we still see is this really bad oscillation. And like, is there really a way to eliminate this oscillation? Not really with the PI controller. And this is kind of what the problem with the PI controller is. It's not really designed for a position set point. You can damp it out a little bit, as Varun's doing, by changing the relative degree between P and I. And this is kind of what you'd expect with this controller. But where PI really shines is if we're trying to do like a velocity tracking task. So we get that down. Yeah, it'll be in this graph. So if you just give it a P, it'll do it steady state. So this is what I mean by steady state error, since I've used that term. So what we're doing now is we're trying to have our set point in velocity. So we're trying to reach a velocity of 1 meter per second. We use our P controller because we have our I set to 0 right now. And the velocity caps out at some point. We're not quite there, but we're better off than we were before with this P controller. But if we add an I term, what you'll see is that it'll actually reach that set point. Because now we have this accumulated error, so over time, as we continue to sit at this cap out point, it'll slowly push us up. This one's a little bit more aggressive, so it does it like almost immediately. But this will handle any like steady state error as we talk about. So this would be something like friction as you were driving along. So this is the concept of a PI controller, and they're really good for like holding an actuator at some fixed location, because it'll handle any of that steady state error of it not quite reaching the correct height, but being pretty close. Due to gravity, yes. Any questions? I lost you completely. Feel free to stop me and ask questions. Okay. So then, like, if we scroll down in this notebook, this will actually just do a full PID. So this has all P, the proportional term, the integral term, and the derivative term. And you can play with all the different ones, both for position set points as well as velocity set points.
So can you do a PID with position?
Yeah, you can do a PID with anything.
Can you do it on here?
Yeah. So the way you'd usually tune the PID is you want to set P to a number. Start off with just P. So everything else to 0 and then just set P. And what you want to see is that you quickly reach your set point. That's kind of what we're seeing here.
So in this graph, if you want to go to position 1, you see the robot's going to get a 1.4, right? What happens if there's a wall at 1.2? Okay. So is overshooting the set point good or bad? Okay. Follow? Okay.
So then, as we was talking, to clarify people on stream, essentially the point was made that if you had a wall at like 1.2, this overshoot would be bad because you're doing it in position. Now your robot has crashed into the wall. So when we tune PID controllers, we set up P so that we get to our set point pretty quick, but you're going to expect some oscillation. The next thing we're going to do is increase D up until the point where our oscillation is like, okay. So maybe it only oscillates to 1.1, so we don't hit that wall anymore. And this just depends on your application and what you're trying to do. And you can kind of keep increasing this. This system's a little janky, so you can get away with weird things, like setting it really, really high. But as you see, as he increases this D term, that oscillation is getting damped out more and more. And this is normally what you'd have for like a position system. What I would recommend is doing some sort of PD controller like this. And you tune it this exact way. You do P, and then you do D. If you had some sort of velocity where you had that steady state error that we talked about earlier, where you kind of cap out at some error that's not exactly what you wanted, you do a PI controller, or a PID controller. So if you scroll down, now we're going to do the same thing, but with a velocity target. So if you tune it for, you increase P, then you increase D, then you increase I so that you stabilize to the correct point.
Can you go back to the previous one once you get this done and show us how they can use PID to go to the position without going over?
Yeah, so the question was, can we get to a position without going over? And that would just be a less aggressive P. So if you decrease your P, sometimes it just depends on your application, right?
We can use where would you use the I in this?
You don't necessarily have to use all 3 in every situation.
Yeah, usually you don't want to. I recommend not using I for the most part. There's a couple of like common issues with I. One of the things called windup, where your integral term just accumulates errors so much over time that you overshoot really bad, which is what you were saying much earlier. But you can like cap that. There's lots of like little hacks you can do on PID. But usually if you're using all the terms without a reason, like don't.
Okay.
Like start off with P, tune P up to a reasonable point, and then that could be capping out below your set point if you're really careful about where you are. Or it could be oscillating over if you just want to get there really quick. Then you do D to handle that, like handle oscillations, or use I to get to the set point. And then if you have like issues with PI going like this, you can try using D to damp that out.
Well, since you mentioned it, one good way of like thinking about whether you want to use I is if you start with your P and you see steady state error, then you know that eventually you're going to need to add I. And since Jason was mentioning it, talking about mechanisms and positioning them, one good place where you would want to use a PI control is if you have a linear slide elevator. The elevator has some weight, and so the motor will always have to hold that weight up. And with a P controller alone, there will be situations where the force applied by the P controller is equal to gravity. So there's a stable point that may not necessarily be at your goal location. So adding the I term in that situation will allow you to overcome gravity and position the elevator wherever you want. So always consider before you start doing your control, like, is there going to be steady state error? If there is, then you would need I. If you don't see any like reasonable reason for steady state error, then you only care about the P and D terms.
I think that covers it. Yeah. I just jumped ahead. So, as I talked about a little bit, so like practical considerations, right? The thing you were saying, I don't cap any of like the accelerations or essentially capping the torque of the motor, so it becomes physically impossible pretty quickly. So you'll want to do that, and it'll give you a little bit different behavior. But most the same rules of thumb apply. And then also I talked about integral windup. So one thing you can do is just cap the integral value. The big thing to watch out for this, and I've tipped over robots multiple times, is if your robot is disabled, but your PID controller is still running, I is just going to continue to build up and get larger and larger and larger. So then when you hit the go button to re-enable the robot, it'll cap off and usually tip over. So integral windup's nice. You want to check to make sure that integral value doesn't build up too large because it'll just overwhelm any other term you have going on. So you can do stuff like only integrate commands if it's within the control limit, or like just cap out integral at a certain value so it doesn't completely override everything. And we've essentially already covered this, so I don't think we need to continue rehashing it. But again, start off with a simple P, increase your P. If you see steady state error, consider an I. If you see a lot of oscillations, consider a D. Most of it's just driven by P. So there are implementations of this. So there is velocity PID in your Talon SRX, and these other motor controllers, and this already exists in WPILib. Depending on what you want, you might have to write it yourselves, and as you can see here, the equations are pretty quick. It's only 3 or 4 lines of code to write PID. So next I'm going to pass it back to Varun to talk about pure pursuit control.
So far, Jason did a great job of covering the first part of robotics, which is finding out where the robot is, and the second part of robotics, which is deciding how much force to apply to the robot in order to get it to move. So now we're going to talk about how you can combine those two building blocks into creating a controller for your robot, which will allow it to smoothly traverse through waypoints. But before I continue, did anyone have any questions about any of the previous sections?
Any extreme questions?
They have been very silent.
Okay. Well, I guess if it's okay, then I'm just going to go ahead and move on. So the first thing you might be tempted to do with the knowledge that you have gained so far is if you want to move through from point A to B, then B to C, then C to D, we're going to string together a bunch of point-to-point motions. So your point-to-point motion is just, I'm starting at point A. I'm going to turn the robot until it points towards point B. I'm going to drive in a straight line for a particular distance. I'm going to stop. I'm going to turn until I'm facing the next place I want to go. And then I'm going to continue driving. And, with the knowledge that you've gained so far, this is pretty effective. You might as well start out trying this if this is your first, time writing some autonomous code. This is a great start. But it has one key drawback, which is the robot has to speed up, go at its, max speed, slow down, and stop in every single segment. And with 15 seconds only in your autonomous period, you're going to waste a lot of time speeding up, slowing down, stopping, speeding up, slowing down, and stopping. This is what that looks like in FRC. This is a 2-cube point-to-point motion-based autonomous. If I guess none of you guys were students in 2018, but this is the game. 2 cubes was considered a pretty good score but some of the best teams out there were able to get 3 or 4. And then there's a gap between the teams that can do 2 and the teams that can do 3 or 4 in autonomous. And the answer is they weren't wasting time stopping after every single point in their motion. So one way that we can approach this is through the pure pursuit algorithm. And the pure pursuit algorithm is just a control algorithm which allows you to smoothly move through a series of waypoints. And so how does it do that? The robot is trying to follow, in a sequence of arcs, it's trying to follow the look-ahead point. So each path segment is just a straight line between 2 consecutive points. And the look-ahead point travels along each of those path segments. And the robot tries to drive in an arc which connects it to the look-ahead point. So that's what you can see on the top right. And then that's an example of the robot moving in that smooth path on the bottom right. So the first thing we need to do is we need to find out where that look-ahead point is. And so here we're going to use some simple geometry and vector math in order to figure that out. So what we formulate this problem as, if we draw the world here, you can see that this is a path segment from point A to point B. And our robot is located at point C. The look-ahead point is a distance L away from the robot, and it lies on the path. So right here, point E. Point E is where we want to be driving towards. So how do we find point E? Well, let's divide this red line here into 2 segments. One segment is X, and one segment is Y. So clearly the distance from A to E is going to be what? Right, X plus Y. The answer's on the slide. So now, maybe since you guys have taken geometry, you'll know, how do we calculate what is X and what is Y? These are some, we love to solve triangles here. This is some geometry problems. First thing we can do is X comes from this perpendicular line drawn here. So from C to the path, this line is perpendicular to the path and connects C to the path. So X is the distance from A to that place where that perpendicular line is drawn. So this diagram should be ringing some bells in your head because it reminds us of one of the things that we did with vectors at the very beginning of this presentation. And that thing is a scalar projection. So if you guys remember, the scalar projection, it comes from the dot product. So we can use the dot product of this vector here in order to find the value of X. So here, the formula is very simple. It's AB hat. Does anyone remember what the hat means?
The unit vector of the A to B.
Right, so the hat means the unit vector. So the unit vector from AB is just a vector that has a length of 1 and points from A to B. And we're going to use the dot product of AB and AC, where AC is the vector which connects the starting point of the path to the location of the robot. So using this formula right here, you can say that x1 times x2 plus y1 times y2 is equal to u dot v times the cosine of the angle between them. And from that we can, just extract x. So now that we've found the x by solving this green triangle here, now we need to solve for y using this blue triangle here. So y, this one's pretty straightforward. You guys remember the Pythagorean theorem. First thing you guys learned in geometry class. But here we need to find first, in order to have this triangle fully specified in order to solve for y, we need to first solve for d. And d is the distance between the path segment and the robot. And luckily for us, we just found x in the previous step. So we can use the Pythagorean theorem twice here. Once to solve for d, and then once we know d, we can calculate y using that formula right there.
Where do we get L from?
So L is look-ahead distance. That is a parameter that you can write yourself. So you actually have to pick how far you want the robot to look ahead. And when you get to the interactive demo, you can see what happens when you choose values of L that are large or small. How does that affect the way the robot tracks the path? But for now, all you need to know is that L is a number that is like you as the programmer will decide. And based on what behavior you want the robot to do, you can change what L is. So now we're going to make a simple approximation that's going to make your life a little bit easier. Remember, we just had to use the Pythagorean theorem twice, once to solve for D and once to solve for Y. But remember, the robot is in location C, which is not on the path. The closer the robot is to the path, the smaller the value of D gets. And when D gets small, what's the relationship between, this has a little bit messed up notation. That should be Y. What do you think is the relationship between L and Y when D is really small? Can anyone tell me what they think?
They should get closer together. They should be equal.
Right. So we can let's think about the extreme case here, right? Y is equal to the square root of L squared minus D squared. Let's say D squared was really small, or even 0. If D squared were 0, then Y would be equal to the square root of L squared, which is just L. So as long as we think that the robot is close enough to the path, we can skip calculating D in the first place and simply say that Y is equal to L. And in that case, the distance between point A and point E is just x plus L. And that means that you take the x plus L and you multiply it by the unit vector AE, which is actually the same as the unit vector AB. And there you go. You've found the location of E. So now that we know where the look-ahead point is, we need to start with step 2 of the pure pursuit algorithm. And step 2 is actually steering the robot into the location of the look-ahead point. So we start with the robot right here, and we have to draw an arc which connects the look-ahead point to the robot. And we do that using this relationship here. Since it's an arc, it's going to have a constant radius. So there's going to be some point, which is a distance of r away from the robot. That's also a distance of r away from the path. And they're connected by another distance L, which is the look-ahead distance of the robot. And I've spared you the trouble and have written out the solution to this right here. But if you guys ever feel like it, you can always verify this using the law of sines. It's just some geometry formula. You can say that the curvature, kappa, which is 1 over the radius, is equal to 2 sine alpha over L. And alpha is the angle error between where the robot is pointed and the look-ahead point. So here the robot might not be always pointing perfectly towards the look-ahead point. So the difference in angle between the robot and the direction of the look-ahead point is alpha. So last thing we need to do is we need to find the wheel velocities which cause the robot to drive along that arc. So here we can use the kinematics of the differential drive, like basically the formulas which define how the velocities of the wheels correspond to the velocity of the robot. Let's let this value delta be equal to v robot, which is the velocity of the robot, whatever speed you want it to go at, times little l, which is the distance between the left side wheel and the right side wheel. All that multiplied by kappa, which is the curvature we just calculated. Then you can simply apply this formula here, and you get the velocity of the left and the velocity of the right wheel. So now those two numbers, you can just plug it into your robot, and it'll drive in that curve. And I did define a new variable here called vrobot. The vrobot is another number that you can just pick for yourself. However, whatever speed you want the robot to run at as it moves along the path, that is vrobot. And so once you pick that number and you pick the look ahead distance, you can just, solve all these formulas, write them in your code, and it just works. So let's recap. What are all of the steps required to follow some sequence of paths or sequence of points to make up your path? First thing you want to do is find the look ahead point. That's like kind of where the robot is going to need to end up. You can steer so that the robot is pointing towards the look ahead point. You want to calculate and then apply the required steering to move towards the look ahead point. And of course, there's a chance that the look ahead point is at the end of the segment. And if it's at the end of the segment, you don't want to keep tracking it. You want to start tracking the next segment. So you can make a smooth transition from the first segment into the second segment. So here you would, in step 3, you can actually implement this however you want. You can either have the robot stop at the end, or you can have it start tracking the next one. But the decision there is up to you as the programmer. And we're going to go into a quick demo just to show off, what happens when you change the velocity in the look ahead distance. Yeah, so unfortunately this notebook isn't as nice as the first one, but it'll generate some nice animations at the bottom. Or will it? There we go. So here's a shape. The robot's kind of going crazy. I think this is the one where the bad look ahead distance. Let's make it. Let's make this. So we'll start with a look ahead distance of 0.5. And unfortunately, it takes a while for the animation to render, so we're going to have to be patient here. But you can see that the robot kind of makes arcs at each of the points, but for most of the segment, it travels perfectly along the segment. And this is like a good behavior, actually, since you can get a smooth transition from one segment of the path to the next one. So now let's try to tune really the only tunable parameter in the pure pursuit control is the look ahead distance. So what do you guys think happens if we make the look ahead distance larger? What sort of behavior do you guys think the robot will take? 5's a little too much. You can make it like 1.5.
So what do you think it's going to do?
Turning prematurely, or
You think it'll turn prematurely?
like,
That's what makes sense.
Relative to the path, how close to the path is it going to stay?
farther.
You think it's going to be farther away from the path?
Because if the
What
look
about you guys?
it's going to figure it
Okay.
Well, let's find out. Yeah, so for those of you guys watching on the stream, the general consensus is that people think the robot is going to be farther away from the path. And you would be pretty much correct. You can see that one key thing to look at is that the robot is going to make much wider arcs when it turns. And so the robot will start turning earlier. It'll make a wide turn rather than with a short look ahead distance, it'll make a sharp turn.
What about the position of the robot at the end of the path?
It'd be farther away because since
No,
it's pretty closer.
it's going to end at the end of the path.
Same place, right?
It's always going to end at the same. It's always going to end at the end of the path. But look at the orientation of the robot.
It's messed up.
It's not pointing straight ahead relative to the path.
So the reason why the robot doesn't line up at the end of the path is because of the look ahead distance. So we noticed when the look ahead distance was small, it was like 0.5. The robot was really tightly tracking the path. And since, like, in general, if the robot is tracking the path tightly, it means that by the time it reaches the end, the chance that it's perfectly aligned with the path is a lot higher. So the look ahead distance is something you can play around with once you've decided what sort of path you want to take. As you guys have probably observed, since you can make tighter turns with a smaller look-ahead distance, you should decide the look-ahead distance based on how tight the turns are in whatever path sequence you want to make. Of course, a sharper turn means the robot actually has to slow down to actually make the turn. Otherwise, it would skid. So there is a trade-off here, which is that the sharper you make your turns, the more you have to slow down at the end. And of course, a look-ahead distance of 0 is essentially the same as point-to-point motion, because you have to make an infinitely tight turn at the end, which requires you to stop completely. So the look-ahead distance kind of lets you choose between whether you want to do this in a point-to-point style, or if you want to do it with like a big arc traveling all the way around. So as you tune that value higher or lower, you'll kind of see how that trade-off plays out in your robot. It actually breaks when it's like too low. Yeah.
So how do you think you guys would get the best of both worlds? If you wanted the robot to be pointed straight with a path at the end, but you wanted the speed of the wider curve?
Yeah, I guess one thing you guys will learn is I know I just talked about the theoretical end case, but really in your code you get a bunch of edge cases that you have to deal with when the look-ahead distance is so small. I guess one other thing that the reason why that happened is because, can you go back to the PowerPoint real quick? Right. So if the look-ahead distance is really small, well, remember that we're trying to find the intersection point between the circle and the line. That's part of part of the calculation we're doing. If L is smaller than D, what do you think happens at that point?
It's not on the line. It's not on the
Right. If L is smaller than D, what happens when you take the square root of a negative number?
Oh, imaginary.
Right. So in reality, this algorithm doesn't work when L is too small. I just talked about the limiting case, which is where L equals 0. But really, that only works when if you started on the path perfectly. If you even start slightly off the path and your L is too small, there will be no solution to this equation, and then your robot will just like not be able to do anything. So I know that there's theoretical limits, and in reality, the practical limit is whether or not the robot is close enough to the path for you to solve this equation in the first place. So that is what you just saw, was the equations being wrong and the simulation not really knowing what to do. I mean, I'm good. You can go back to the presentation.
That's cool. Yeah. Is this code on GitHub?
No. Yes. I mean, the code is, the link to the notebook is freely available.
All right. They're going to post this will be posted.
Oh, cool.
So that was the end of my presentation. Here we have the emails for the three of us. If you have any questions relating to the content that we talked about today, feel free to shoot us an email. These are Georgia Tech emails, and we'll be happy to help you with any problems you might have in your implementation. Or if you have some clarifications you want on the content we covered today, also happy to give you any clarifications. Yeah, or if you have access issues with either of the notebooks that we showed, yeah, that'll also be, any questions that you might have, we can resolve it if you just email us. So just to wrap it up, thank you guys so much for coming. I hope that you found all these building blocks of an autonomous program to be really useful. And I sure hope that in the coming season, you guys will be able to put together at least some of these, if not all three of them, and we're going to get to see some really cool autonomous programs this year. So thank you guys.
This is gonna forward that. They covered this very briefly.
No questions?
The other one was really just for.
I think there were a lot of issues with the streams at first. So a lot of people like just didn't show up.
Yeah, I think if you know, you're not there when you don't think you're gonna be there, then they kind of get.
I mean, they're like, this dude, somebody was like, thank you so much, but they didn't ask me.
Once it gets, what is it, 1 degree?
Yeah, these stuff.
Oh, and you have to use it personal email.
And then pure C. So you're driving. Cool. If I've got a path.
It comes to I as well.
If I do a path, stop, turn.
Instead, which is like 0 point something something, so I just like add one to that and then multiply, so it's like a little increase. It's just like, I'll just, go back and forth. Yeah, I say, interesting. And it doesn't quickly, it's not even that big of a deal, right? But at the end of the day, it completes it and.
Thank you so much.
That was advice for somebody doing an RC or for?